Now that we understand stream ciphers, we're going to move on and talk about a more powerful primitive called a block cipher. So a block cipher is made up of two algorithms, E and D. These are encryption and decryption algorithms. And both of these algorithms take as input a key K. Now the point of a block cipher is that it takes an n-bit plaintext as input, and it outputs exactly the same number of bits as output. So it maps n bits of input to exactly n bits of output. Now there are two canonical examples of block ciphers. The first one is called triple des. In triple des, the block size, namely the number of input bits, is 64. So triple des will map 64-bit blocks to 64-bit blocks, and it does it using a key that's 168 bits long. We're going to talk about how triple des is built in the next segment. Another block cipher, which is more recent, is called AES. Now AES has slightly different parameters. So here the block size is 128 bits. So AES will map 128 bits of input to 128 bits of output. And it actually has three possible sizes of keys, and I wrote down these sizes over here. Basically, the longer the key, the slower the cipher is, but presumably the more secure it is to break. And we're going to talk about what it means for block ciphers to be secure in just a minute. Now, block ciphers are typically built by iteration. They take in as input a key K. For example, in the case of AES, the key could be 128 bits long. And the first thing that happens to the key is it gets expanded into a sequence of keys, K1 to Kn, called round keys. Now, the way the cipher uses these round keys is by iteratively encrypting the message again and again and again using what's called a round function. So here we have this function R that takes two inputs. This function R is going to be called a round function. It takes as input the round key, and it takes as input the current state of the message. So here we have our input message. Say for AES, the message would be 128 bits exactly, because each block in AES is exactly 128 bits. And then the first thing that happens is we apply the first round function using the key K1 to the message. And we get some new message out as a result. Then we take this message M1, we apply the next round function to it using a different key, using the key K2, and we get the next round message out. And so on and so forth until all the rounds have been applied. And then the final output is actually the result of the cipher. And again, this would be also in the case of AES, this was 128 bits. And the resulting ciphertext would also be 128 bits. Now, different ciphers have different number of rounds, and they have different round functions. So for example, for triple des, the number of rounds is 48, and we're going to see exactly how the round function for triple des works. For AES, for example, the number of rounds is only 10, and again, we're going to look at how the round functions for AES work as well in just a minute. Before we do that, I just wanted to mention performance numbers. So you can see here, these are the performance numbers for the two typical block ciphers, triple des and AES. And these are the corresponding numbers for the stream ciphers that we looked at in the previous module, RC4, Salsa, and Sosa Manuk. And you can see that the block ciphers are considerably slower than stream ciphers, but we'll see that we can do many things with block ciphers that we couldn't do very efficiently with constructions like RC4. Now, my goal for this week is to show you how block ciphers work, but more importantly, I want to focus on showing you how to use block ciphers correctly for either encryption or integrity or whatever application you have in mind. So to show you how to use block ciphers correctly, it actually makes a lot of sense to abstract the concept a little bit so that we have kind of a clean, abstract concept of a block cipher to work with, and then we can argue and reason about what constructions are correct and what constructions are incorrect. And so an abstraction, it's a very elegant abstraction of a block cipher, is what's called a pseudo-random function and a pseudo-random permutation. So let me explain what these things are. So a pseudo-random function basically is defined over a key space, an input space, and an output space. And all it is basically a function that takes a key and an input as inputs and outputs some element in the output space. Okay, so it takes an element in K, an element in X, and outputs an element in Y. And the only requirement, essentially, is that there's an efficient way to evaluate the function. For functions, we're not requiring that they be invertible. We just need them to be evaluatable given the key and the input X. Now, a related concept that more accurately captures what a block cipher is called a pseudo-random permutation. So a pseudo-random permutation is, again, defined over a key space and then just a set X. And what it does is it takes an element in the key space and an element in X and outputs basically one element in X. Now, as usual, the function E should be easy to evaluate, so there should be an algorithm to evaluate the function E. But more importantly, once we fix the key k, it's important that this function e be one-to-one. In other words, if you think of the space x as a set here, and here's the same set x again, then basically the function e, what it does is it's a one-to-one function, so every element in x gets mapped to exactly one element in x. And then because it's one-to-one, of course it's also invertible. So given some output, there's only one input that maps to that output, and the requirement is that there's an efficient inversion algorithm, call it D, that given a particular output, will output the original preimage that mapped to that output. So really a pseudo-random permutation captures very accurately and syntactically what a block cipher is, and often I'll use the terms interchangeably, either a block cipher or a pseudo-random permutation. I'll use whichever term depending on the context where we're discussing things. Okay, so we have two examples, as we said, of pseudo-random permutations, triple des and AES. Say for AES 128, the key space would be 128 bits, and the output space would be 128 bits. For triple des, as we said, the block size is only 64 bits, and the key size is 168 bits. Okay, so we'll use these running examples actually throughout, so whenever I say a PRP, concretely, you should be thinking AES or triple des. Now, one thing that I wanted to point out is that, in fact, any pseudo-random permutation, namely any block cipher, you can also think of it as a PRF. In fact, a PRP is a PRF that has more structure. In particular, PRP is a PRF where the input space and the output space are the same, so x is equal to y, and in fact is efficiently invertible once you have the secret key k. Okay, so in some sense, a PRP is a special case of a PRF, although that's not entirely accurate, and we'll see why in just a second. So far we just described the kind of the syntactic definition of what is a pseudo-random permutation and a pseudo-random function. So now let's talk about what it means for a PRF or a PRP to be secure, and this concept will essentially capture what it means for a block cipher to be secure. Okay, so this is why I wanted to show you these definitions before we look at actual block cipher constructions, so at least it's clear in your mind what it is we're trying to construct. Okay, so here we have a PRF, and I'm going to need a little bit of notation, not too much though, so I'm going to need to define the set funds of x, y. This is basically the set of all functions from the set x to the set y. Denoted here as a big circle, funds of x, y. Now this set is gigantic. Its size is basically, the size of y to the size of x. So for example, for AES, remember both x and y would be 2 to the 128. So for AES, the size of the set is enormous. It'll be 2 to the 128 times 2 to the 128. So it's kind of a double exponential. So this is a gigantic number. This is more particles than there are in the universe. But regardless, we can kind of think of this set abstractly. We never have to kind of write it down. We can just keep it in our head and not worry about computing on it. So this is a particular gigantic set of the set of all functions from x to y. Now we're going to look at a much smaller set of functions, namely I'll call this set S sub f, and that's going to denote the set of all functions from x to y that are specified by the PRF as soon as we fix a particular key k. Okay, so we fix the key k, we let the second argument float, and that basically defines a function from x to y. And we're going to look at the set of all such functions for all possible keys in the key space. Okay, so if you think about it again, for AES, if we're using 128-bit keys, the size of this, I'll say SAES, is basically going to be 2 to the 128. So much, much, much smaller than the set of all possible functions from x to y. And now we say that a PRF is secure basically if a random function from x to y, so literally we pick some arbitrary function in this gigantic set of all functions from x to y, and we say that the PRF is secure if in fact a random function from x to y is indistinguishable from a pseudo-random function from x to y, namely when we pick a random function from the set SF. Okay, so more precisely, basically, again, the uniform distribution on the set of pseudo-random function is indistinguishable from the uniform distribution on the set of all functions. Let me be just a little bit more precise, just to give you a little bit more intuition about what I mean by that, and then we'll move on to actual constructions. So let me be a bit more precise about what it means for a PRF to be secure. And so what we'll do is basically the following. So we have our adversary just trying to distinguish truly random function from a pseudo-random function. So what we'll do is we'll let him interact with one of the two. So here in the top cloud, we're choosing a truly random function. In the bottom cloud, we're just choosing a random key for a pseudo-random function. And now what this adversary is going to do is he's going to submit points in x. So he's going to submit a bunch of x's. In fact, he's going to do this again and again and again. So he's going to submit x1, x2, x3, x4. And then for each one of those queries, we're going to give him either the value of the truly random function at the point x or the value of the pseudo-random function at the point x. Okay, so the adversary doesn't know which one he's getting. By the way, for all queries, he's always getting either the truly random function or the pseudo-random function. In other words, he's either interacting with a truly random function for all his queries, or he's interacting with a pseudo-random function for all his queries. And we say that the PRF is secure if this poor adversary can't tell the difference. He cannot tell whether he's interacting with a truly random function or interacting with a pseudo-random function. Okay, and we're going to come back actually later on and define PRFs more precisely. But for now, I wanted to give you the intuition for what it means for a PRF to be secure, so you'll understand what it is that we're trying to construct when we construct these pseudo-random functions. And I should say that the definition for a pseudo-random permutation is pretty much the same, except instead of choosing a random function, we're going to choose a random permutation on the set x. In other words, a random one-to-one function on the set x. The adversary can either query this random function on the set x, or he can query a pseudo-random permutation, and the PRP is secure if the adversary cannot tell the difference. Okay, so again, the goal is to make these functions and permutations look like truly random functions of permutations. Okay, so let's look at a simple question. So suppose we have a secure PRF. So we know that this PRF f happens to be defined in the set x, and it so happens, it outputs 128 bits every time. It so happens that this PRF cannot be distinguished from a truly random function from x to 0, 1 to the 128. Now we're going to build a new PRF. Let's call this PRFG. And the PRFG is going to be defined as follows. We say if x is equal to 0, always output 0. Otherwise, if x is not equal to 0, just output the value of f. So my question to you is, do you think this G is a secure PRF? Well, so the answer, of course, is that it's very easy to distinguish the function G from a random function. All the adversary has to do is just query the function at x equals 0. For a random function, the probability that the result is going to be 0 is 1 over 2 to the 128. Whereas for the pseudo-random function, he's always going to get 0. Because at 0, the function is always defined to be 0 no matter what the key. And so all he would do is he would say, hey, I'm interacting with a pseudo-random function if he gets 0 at x equals 0. And he'll say, I'm interacting with a random function if he gets non-zero at x equals 0. So it's very easy to distinguish this G from random. So what this example shows is that even if you have a secure PRF, it's enough that on just one known input, the output is kind of not random. The output is fixed. And already the entire PRF is broken, even though you realize everywhere else the PRF is perfectly indistinguishable from random. Okay, so just to show you the power of PRF, let's look at a very easy application. I want to show you that in fact pseudo-random functions directly give us a very simple pseudo-random generator. Okay, so let's assume we have a pseudo-random function. So this one happens to go from n bits to n bits. And then let's define the following generator. Its seed space is going to be the key space for the PRF, and its output space is going to be basically t blocks of n bits each. Okay, so you can see the output is a total of n times t bits for some parameter t that we can choose. And it turns out basically you can do this very simple construction. This is sometimes called counter mode, where essentially you take the PRF and you evaluate it at 0, you evaluate it at 1, you evaluate it at 2, at 3, at 4, up to t, and you concatenate all these values. That's the generator. Okay, so we basically took the key for the PRF and we expanded it into n times t bits. Okay? A key property of this generator is that it's parallelizable. And what I mean by that is if you have two processors or two cores that you can compute on, then you can have one core compute the even entries of the output, and you can have another core compute the odd entries of the output. So basically, if you have two cores, you can make this generator run twice as fast as it would if you only have a single core. So the nice thing about this is, of course, we know that pseudo-random generators give us stream ciphers, and so this is an example of a parallelizable stream cipher. And I just wanted to point out that many of the stream ciphers that we looked at before, for example RC4, those were inherently sequential. So even if you had two processors, you couldn't make the stream cipher work any faster than if you just had a single processor. Now the main question is, why is this generator secure? And so here I'm only going to give you a little bit of intuition, and we're going to come back and argue this more precisely later on. But I'll just say that security basically follows directly from the PRF property. And the way we reason about security is we say, well, this PRF by definition is indistinguishable from a truly random function on 128 bits. So in other words, if I take this generator and instead I define a generator using a truly random function, in other words, I'll write the output of the generator as f of 0 concatenated f of 1 and so on and so forth, using a truly random function, then the output of the generator using the truly random function would be indistinguishable from the output of the generator using a pseudo-random function. That is the essence of the security property of a PRF. But with a truly random function, you notice that the output is just truly random, because for a truly random function, f of 0 is a random value, f of 1 is an independent random value, f of 2 is an independent random value, and so on and so forth. So the entire output is a truly random output. And so with a truly random function, this generator produces truly random output and is therefore a perfectly secure generator. And so you see how the PRF security property lets us argue security. Basically, we argue that when we replace the PRF with a truly random function, the construction is necessarily secure, and that says that the construction with a pseudo-random function is also secure. Okay, and we're going to see a couple more examples like this later on. So now you understand what a block cipher is, and you have intuition for what security properties it's trying to achieve. And in the next segments, we're going to look at constructions for block ciphers. So now that we understand what block ciphers are, let's look at a classic example called the data encryption standard. So just a quick reminder, block ciphers basically map n bits of input to n bits of output. And we talked about two canonical examples, triple DES and AES. In this segment, we're going to talk about DES, and we'll talk about triple DES actually in the next segment. And then I also mentioned before that block ciphers are often built by iteration. In particular, we're going to look at block ciphers that are built by a form of iteration where a key k is first expanded into a bunch of round keys, and then a round function is applied to the input message again and again and again. And essentially, after all these round functions are applied, we obtain the resulting ciphertext. Okay, and again, we're going to look at how DES, the data encryption standard, uses this format. I just want to be clear that in fact, to specify a block cipher of this type, one needs to specify the key expansion mechanism, and one needs to specify the round function. In the segment here, I'm going to focus on the round function, and I'm not going to talk much about key expansion, but I just wanted to mention that in fact, key expansion is also a big part of describing how a block cipher works. Okay, so let's talk about the history of DES. Essentially, in the early 1970s, IBM realized that their customers are demanding some form of encryption. And so they formed a crypto group, and the head of that group was Horst Feistel, who in the early 70s designed a cipher called Lucifer. Now it's interesting, in fact Lucifer had a number of variations, but one of the later variations in fact had a key length that was 128 bits and a block length that's also 128 bits. Okay? In 1973, the government realized that it's buying many commercial off-the-shelf computers, and so it wanted its suppliers to actually have a good crypto algorithm that they could use in products sold to the government. So in 1973, the National Bureau of Standards, as it was called at the time, put out a request for proposals for a block cipher that's going to become a federal standard. And in fact, IBM submitted a variant of Lucifer. That variant actually went through some modification during the standardization process. And then finally, in 1976, the National Bureau of Standards adopted DES as a federal standard. And in fact, for DES, it's interesting that the key length was far reduced from Lucifer. It's only 56 bits, and the block length was also reduced to 64 bits. And in fact, these decisions, especially the decision to reduce the key length, is kind of the Achilles heel of DES and was a source of many complaints over its life. In particular, already back in 1997, DES was broken by exhaustive search, meaning that a machine was able to search through all 2 to the 56 possible keys to recover a particular challenge key. And in fact, we're going to talk about exhaustive search quite a bit. It's quite an interesting question, and there are various ways to defend against exhaustive search. And basically this 1997 experiment kind of spelled the doom of DES. It meant that DES itself is no longer secure, and as a result, the National Institute of Standards, as it became known, issued a request for proposals for a next generation block cipher standard, and in 2000 it standardized on a cipher called Rindell, which became the Advanced Encryption Standard, AES, and we'll talk about AES later on. But in this segment I want to describe how DES works. Now DES as a cipher, it's an amazingly successful cipher. It's been used in banking industry. In fact, there's a classic network called the Electronic Clearinghouse, which banks use to clear checks with one another, and DES is used for integrity in those transactions. It's also used in commerce. In fact, it was very popular up until recently as the main encryption mechanism for the web. Of course, now that's been replaced with AES and other ciphers. Overall, it's a very successful cipher in terms of deployment. DES also has a very rich history of attacks, which we'll talk about in the next segment. Okay, so now let's talk about the construction of DES. So the core idea behind DES is what's called a Feistel network, due to Horst Feistel. And basically it's a very clever idea for building a block cipher out of arbitrary functions f1 to fd. Okay, so imagine we have these functions f1 to fd that happens to map n bits to n bits. Now these are arbitrary functions. They don't have to be invertible or anything. What we want to do is build an invertible function out of those d functions. And the way we'll do it is by building a new function, we'll call it capital F, that maps 2n bits to 2n bits. And the construction is described right here. So here we have our input. You notice there are two blocks of n bits. In other words, the input is actually 2n bits. R and L stand for right and left. Typically people describe a Feistel network from top to bottom, in which case these n bits really would be right and left. But here it's more convenient for me to describe it horizontally. So if we follow the R input, you realize it basically gets copied into the L output without any change at all. Okay? However, the L input is changed somewhat. Basically what happens is the R input is fed into the function f1, and the resultant is XORed with L0, and that becomes the new R1 input. Okay, so this is called one round of a Feistel network, and it's done using the function f1. Now we do this again with another round of the Feistel network with the function f2, and we do it again and again and again till we get to the last round, and we do it again with the function fd, and finally the output is rd ld. Okay, so if you like, we can write this in symbols, that basically li is simply equal to ri minus 1, and ri, let's see, that's the more complicated one, ri is equal, well, let's just follow the lines here, ri is just equal to fi applied to ri minus 1 XOR li. Okay, so and this is basically I goes from 1 to d. So this is the equation that defines a Feistel network mapping a 2n-bit input to 2n-bit output. So here we have the, again, I just copied the picture of the Feistel network, and the amazing claim is that in fact it doesn't matter which functions you give me. For any functions f1 to fd that you give me, the resulting Feistel network function is in fact invertible. And the way we're going to prove that is basically we're going to construct an inverse, because not only is it invertible, it's efficiently invertible. So let's see. So let's look at one round of a Feistel network. So here, this is the input, Ri, Li, and this is the output, Ri plus 1, Li plus 1. And now what I'm going to ask you is to invert this. So let's see. So suppose now the input that we're given is Ri plus 1, Li plus 1. And we want to compute Ri, Li. So we want to compute the round in the reverse direction. So let's see if we can do it. Well, let's look at Ri. So Ri is very easy. Basically, Ri is just equal to Li plus 1. So Li plus 1 just becomes Ri. But now let me ask you to write the expression for Li in terms of Ri plus 1 and Li plus 1. So I hope everybody sees that basically Li plus 1 is fed into the function Fi plus 1. The result is XORed with Ri plus 1, and that gives the Li input. So this is the inverse of one round of a Feistel network. And if we draw this as a diagram, let's just write the picture for the inverse. So here you notice the input is Ri plus 1, Li plus 1, and the output is Ri, Li, right? So we're inverting the round. So you notice that the inverse of a Feistel round looks pretty much the same as the Feistel round in the forward direction. It's literally, just for a technical reason, it's kind of the mirror image of one another, but it's basically the same construct. And when we put these inverted rounds back together, we essentially get the inverse of the entire Feistel network. So you notice we start off with round number d, with the inverse of round number d, then we do the inverse of round number d minus 1, and so on and so forth, until we get to the inverse of the first round, and we get our final output, which is R0, L0. Right? This is the input, and we manage to invert basically RD, LD, and get R0, L0. And the interesting thing is that basically the inversion circuit looks pretty much the same as the encryption circuit, and the only difference is that the functions are applied in reverse order. Right? We started with FD and ended with F1, whereas when we were encrypting, we started with F1 and ended with FD. So for hardware designers, this is very attractive because basically if you want to save hardware, you realize that your encryption hardware is identical to your decryption hardware. So you only have to implement one algorithm and you get both algorithms the same way. The only difference is that the functions are applied in reverse order. Okay, so this Feistel mechanism is a general method for building invertible functions from arbitrary functions f1 to fd. And in fact, it's used in many different block ciphers, although interestingly, it's not actually used in AES. So there are many other block ciphers that use a Feistel network. Of course, they differ from DES in the functions f1 to fd, but AES actually uses a completely different type of structure that's actually not a Feistel network. We'll see how AES works in a couple of segments. So now that we know what Feistel networks are, let me mention an important theorem about the theory of Feistel networks that shows why they're a good idea. This theorem is due to Luby and Rockoff back in 1985, and it says the following. Suppose I have a function that is a secure pseudo-random function. Okay, so it's indistinguishable from random and happens to act on n bits. So it maps n bits to n bits and uses a key k. Then it turns out that if you use this function in 3 rounds of a Feistel network, what you end up with is a secure pseudo-random permutation. In other words, what you end up with is an invertible function that's indistinguishable from a truly random invertible function. And I hope you remember that the definition of a secure block cipher is that it needs to be a secure pseudo-random permutation. So what this theorem says is if you start with a secure pseudo-random function, you end up with a secure block cipher. Basically, that's what this says. Now let me explain in a little bit more detail what's actually going on here. So essentially, the PRF is used in every round of the Feistel network. So in other words, here what's actually computed is the PRF using one secret key, K0. Here what's computed is the PRF using a different secret key, of course applied to R1. And here we have yet another secret key, K1 applied, K2 applied to R2. And you notice this is why basically this Feistel construction uses keys in K cubed. In other words, it uses 3 independent keys. So it's very important that the keys are actually independent. So really we need 3 independent keys. And then we end up with a secure pseudo-random permutation. Okay, so that's the theory behind Feistel networks. And now that we understand that, we can actually look at the specifics of DES. So DES is basically a 16-round Feistel network. Okay, so there are functions f1 to f16 that map 32 bits to 32 bits, and as a result, the DES itself acts on 64-bit blocks, 2 times 32. Now, the 16 round functions in DES are actually all derived from a single function f, just used with different keys. So in fact, these are the different round keys. So ki is a round key, and it's basically derived from the key k, derived from the 56-bit DES key k. Okay, and I'll describe what this function f is in just a minute. But basically, you see that by using 16 different round keys, we get 16 different round functions, and that gives us the Feistel network. So just at a high level, how the DES works, basically you have a 64-bit input. The first thing it does is this initial permutation that just permutes the 64 bits around, namely it maps bit number 1 to bit number 6, bit number 2 to bit number 17, and so on. This is not for security reasons, this is just specified in the standard. Then we go into the 16-round Feistel network that actually you now know how it works. Basically uses the function f1 to f16 as specified before. And then basically we have another permutation. This is called the final permutation. That's just the inverse of the initial permutation. Again, it just permutes bits around. This is not necessary for security reasons. And then we finally get the final outputs. Okay, now as we said, there's a key expansion step, which I'm not going to describe. But basically this 56-bit DES key is expanded into these round keys, where each round key is 48 bits. Okay, so we have 16 48-bit round keys, and they're basically used in the 16 rounds of DES. And then when you want to invert the cipher, all you do is you use these round keys, these 16 round keys, in reverse order. Okay, so now that we understand the DES structure, the only thing that's left to do is specify the function capital F. So let me explain how this function works. So basically it takes as inputs its 32-bit value, let's call it X, but in reality you remember this is R0, R1, R2, R3, and so on and so forth. These are 32-bit values. And then it takes also a 48-bit round key. So here we have our key Ki, which happens to be 48 bits. The first thing it does is it goes through an expansion box. And this expansion box basically takes 32 bits and maps them into 48 bits. Now all the expansion box does is just replicate some bits and move other bits around. So for example, bit number 1 of X is replicated into positions 2 and 48 in the output. Bit number 2 of X is positioned in as bit number 3 of the output. And so on and so forth. Just by replicating some of the bits of X, we expand the input into 48 bits. The next thing we do is we compute an XOR with a round key. Sometimes people say that cryptographers only compute XORs. This is an example of that, where, well, we just do XORs in this function. And then comes the magic of DES, where actually these 48 bits are broken into 8 groups of 6 bits. 6, 7, 8. And so let me draw. And then what happens is, so each one of these wires is 6 bits. And then they go into what are called S boxes. And I'll explain the X boxes in just a minute. The X boxes are kind of the smarts of DES. S8. And then the S boxes basically map 6 bits to 4 bits. So the outputs of the S boxes are these 4 bits. They're collected. This gives us 32 bits, right? 8 groups of 4 bits gives us 32 bits. And then finally, this is fed into yet another permutation, which just maps the bits around. So for example, bit number 1 will go to bit number 9, bit number 2 will go to bit number 15, and so on. So it just permutes the 32 bits around, and that's the final 32-bit output of this F function. Okay? So by using different round keys, essentially we get different round functions, and that's how we form the 16 round functions of DES. Now, the only thing that's left to specify are these S boxes. So the S boxes literally are just functions from 6 bits to 4 bits, and they're just implemented as a lookup table, right? So describing a function from 6 bits to 4 bits basically amounts to writing the output of the function on all 2 to the 6 possible inputs. 2 to the 6 is 64, so we just have a table that literally contains 64 values, where each value is 4 bits. So here's an example. This happens to be the 5th S box. And you see that this is a table that contains 64 values, right? It's 4 by 16. So 64 values. And for example, if you want to look at the output that corresponds to 0, 1, 1, 0, 1, 1, okay, then you look at these 2 bits. This is 0, 1. And you look at these 4 bits. This is 1, 1, 0, 1. And you see that the output is 1, 0, 0, 1. The 4 bits output 1, 0, 0, 1. Okay, so the S boxes are just implemented as these tables. Now the question is, how are these S boxes chosen? How are these tables actually chosen by the designers of DES? To give you some intuitions for that, let's start with a very bad choice for S boxes. So imagine the S boxes were linear. What do I mean by that? I mean that imagine that these 6-bit inputs literally were just XORed with one another in different ways to produce the 4-bit outputs. Okay, another way of writing that is that we can write the S box as a matrix vector product. So here you have the matrix AI and the vector, the 6-bit vector X. And you can see that if we write this matrix vector product, basically we take the inner product of this vector with the input vector. Remember, these are all bits. So the 6-bit vector, inner product, another 6-bit vector, and we do that modulo 2, you realize basically what we're computing is x2 XOR x3. Right? Because only position 2 and position 3 have 1s in it. And similarly, the next inner product will produce x1, x4, x4, XOR x5, and so on and so forth. Okay, so you can literally see that if the S boxes are implemented this way, then all they do is just apply the matrix A to the input vector x, which is why we say that in this case the S boxes are completely linear. Now I claim that in fact if the S boxes were linear, then DES would be totally insecure. And the reason is, if the S boxes are linear, then all that DES does is just compute XOR of various things and permute and shuffle bits around. So it's just XORs and bit permutations, which means that as a result, all of DES is just a linear function. In other words, there will be a matrix B of these dimensions. Basically, it's a matrix B that has width 832. Basically, what I would do is I would write the 64-bit message plus the 16 round keys as one long vector, right? So the message is 64 bits, and there are 16 round keys, each one is 48, and that, if you do the math, it's basically 832. Okay, so I write these guys, the keys and the message, as one long vector, and then there would be this matrix that essentially, when you compute these matrix vector products, essentially you get the different bits of the ciphertext. So there's 64 of these rows, and as a result you get 64 bits of ciphertext. Okay, so this is what it means for DES to be linear. So if you think a little bit about this, you realize the S boxes are the only nonlinear part of DES. So if the S boxes were linear, then the entire circuit is linear, and therefore it can be expressed as this matrix. Now, if that's the case, then DES would be terrible as a secure pseudo-random permutation. And let me give you a very simple example. Basically, if you take the XOR of 3 outputs of DES, well, let's think what that means. Basically, we would be looking at B times the matrix B that defines DES times one vector, XOR B times another vector, XOR B times a third vector. We can take the B out of the parentheses, so we'd be basically doing B times this vector over here, but of course K XOR K XOR K XOR K, this is just K. And so if you think about what that means, basically we just got back DES of K at the point M1 XOR M2 XOR M3. But this means that now DES has this horrible relation that can be tested, right? So basically if you XOR the output of 3 values M1, M2, and 3, you'll get the value of DES at the point M1 XOR M2 XOR M3. Now this is not a relation that's going to hold for a random function. A random function is not going to satisfy this equality, and so you get a very easy test to tell you that DES is not a random function. And in fact, it's not even, maybe you can take that as a small exercise, it's not even difficult to see that given enough input-output pairs, you can literally recover the entire secret key. Yeah, you just need 832 input-output pairs, and you'll be able to recover the entire secret key. And so if the S boxes were linear, DES would be completely insecure. It turns out, actually, even if the S boxes were close to being linear, in other words, the S boxes were linear most of the time, so maybe for 60 out of the 64 inputs, the S boxes were linear, it turns out that would also be enough to break DES, and we're going to see why later on. In particular, if you choose the S boxes at random, it turns out they'll tend to be somewhat close to linear functions. As a result, you'll be able to totally break DES. You'll just be able to recover the key in basically very little time. And so the designers of DES actually specified a number of rules they use for choosing the S boxes. And it's not surprising, the first rule is that these functions are far away from being linear. Okay, so in other words, there is no function that agrees with a large fraction of the outputs of the S box. And then there are all these other rules. For example, they're exactly 4-to-1 maps, right? So every output has exactly 4 preimages, and so on and so forth. So we understand now why they chose the S boxes the way they did. And in fact, it's all done to defeat certain attacks on DES. Okay, so that's the end of the description of DES. And then in the next 2 segments, we're going to look at the security of DES. Now that we understand how DES works, let's look at a few attacks on DES. And we're going to start with an attack called exhaustive search. So our goal here is basically that given a few input-output pairs, MICI, our goal is to find the key that maps these M's to the C's. In other words, our goal is to find the key that maps M1, M2, M3 into C1, C2, C3. And as I said, our goal is to find the key that does this mapping. The first question is, how do we know that this key is unique? And so let's do a little bit of analysis to show that, in fact, just one pair is enough to completely constrain a DES key, and that's why this question makes sense. Okay, so let's see. So we're going to prove this simple lemma. Now let's assume that DES is what's called an ideal cipher. So what is an ideal cipher? Basically, we're going to pretend like DES is made up of random invertible functions. In other words, for every key, DES implements a random invertible function. Since there are 2 to the 56 keys in DES, we're going to pretend like DES really is a collection of 2 to the 56 functions that are invertible from 0164 to 0164. Okay, so of course DES is not a collection of 2 to the 56 random functions, but we can idealize the cipher and pretend that it is such a collection. Then what can we say? Then in fact it turns out that just given one message and ciphertext, you just give me one pair, message and ciphertext, there is already only one key that maps this message to that ciphertext. So already, just given one pair, M and C, I can ask you, find me the key that maps M to C, and the solution is very likely to be unique. In fact, it's going to be unique with probability roughly 99.5%. I should say that this statement is true for all M and C, and the probability is just over the choice of the random permutation that make up the cipher. So let's do the proof. This is fairly straightforward. So what we're basically asking is, what's the probability that there exists some key that's not equal to K, such that, well, C we know is equal to DES of K comma M, by definition of C and M, but we're asking how likely is it that there's this other key K prime that also satisfies this equality. You realize that if this is true, if such a key K prime exists, then just given M and C, you can't decide whether the right key is K or K prime, because both of them work. Okay, but I want to argue that this happens with low probability. Well, so what does it mean that there exists a key K prime that satisfies this relation? Well, we're asking what's the probability that the first key, the all zero key satisfies it, or the second key satisfies it, or the third key satisfies it, and so on and so forth. So by the union bound, we can bound this probability by the sum over all keys K prime, over all 56-bit keys, of the probability that des Km is equal to des K prime M. Okay, so we're asking basically, what is this probability for a fixed key K prime that it happens to collide with the key K at the message M? Well, let's think about this for a second. Let's fix this value. Let's suppose it's some fixed value. And then we're asking, how likely is it that a random permutation pi K prime at the point M happens to produce exactly the same output as the key K at the point M? Well, it's not difficult to answer and see that in fact this is, for a single key K prime, the probability is at most 1 over 2 to the 64. Right? There are 2 to the 64 possible outputs for the permutation. What's the probability that it lands exactly on this output? Well, it's 1 over 2 to the 64. And we're summing over all 2 to the 56 keys. So we just multiply the 2. We get 1 over 2 to the 8, which is basically 1 over 256. Okay? So the probability that the key is not unique is 1 over 256. Therefore, the probability that it is unique is 1 minus that, which is 99.5%. Okay, so already, if you give me one plain text ciphertext pair, the key is completely determined. There's only one key that will map that plain text to that ciphertext, and the question is just, can you find that key? Now, it turns out, in fact, if you give me two pairs, so you give me M1 and M2, and their corresponding outputs, C1 and C2, the probability, basically, just do exactly the same analysis, the probability basically becomes 1, that there's only one such key. Okay, essentially, this is very, 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 very close to 1, and basically it says given two pairs, it's very, very likely that only one key will map this pair of messages to this pair of ciphertexts, and as a result, again, we can ask, well, find me that unique key. And by the way, the same is true for AES. If you look at AES 128, again, just given two input-output pairs, there's going to be only one key with very high probability. So essentially now we can ask for this exhaustive search problem. I give you 2 or 3 pairs, and I ask you, well, find me the key. So how are you going to do it? Well, you're going to do it by exhaustive search, essentially by trying all possible keys one by one until you find the right one. So this is what's known as the DES challenge. So let me explain how the DES challenge worked. The challenge was issued by a company called RSA. And what they did is basically they published a number of ciphertexts, but 3 of the ciphertexts had known plaintexts. So in particular, what they did is they took the message here, the unknown message is : and you can see they broke it up into blocks. If you look at these These are basically 8-byte blocks. 8 bytes, as you know, is 64 bits. Right? So each one of these is 64 bits. And then they encrypted them using a secret key. They encrypted all using the same secret key to get kind of 3 ciphertexts. So this gives us 3 plaintext ciphertext pairs. And then they gave us a whole bunch of other ciphertexts, you know, C4, C5, C6. And the challenge was decrypt these guys using the key that you found from an exhaustive search over the first 3 pairs that you were given. Okay. So that was called the DES challenge. And let me tell you a little bit about how long it took to solve it. So interestingly, in 1997, using an internet search, using distributed.net basically, they were able to search through enough of the key space to find the correct key in about 3 months. You realize the key space has size 2 to the 56, but on average you only have to search through half the key space to find the key, and so it took them 3 months. Then kind of a miraculous thing happened. The EFF actually contracted Paul Kocher to build special purpose hardware to break DES. This was a machine called DeepCrack. It cost about $250,000, and it broke the next DES challenge in only 3 days. Interestingly, by the way, RSA said that they would pay $10,000 for each solution of the challenge, so you can see that this is not quite economical. They spent $250K, they got $10,000 for solving the challenge. The next thing that happened is in 1999, RSA issued another challenge, and they said, well, you got to solve it in half the time of the previous solution. And so using both DeepCrack and the internet search together, they were able to break DES in 22 hours. So the bottom line here is essentially DES is completely dead. Essentially, if you forget or you lose your DES 56-bit key, don't worry. Within 22 hours, you can actually recover it. And in fact, anyone can recover it. And so DES essentially is dead and no longer secure. And just kind of a final nail in the coffin, as hardware technology improved, there was another project called Copacabana. They used FPGAs, just off-the-shelf FPGAs, only 120 FPGAs. It only cost $10,000, and they were able to do an exhaustive key search in about 7 days. So very, very cheap hardware, just off the shelf. You can break DES already very quickly. So the lesson from all this is essentially 56-bit ciphers are totally, totally dead. And so the question is what to do. People really like DES. It was deployed in a lot of places. There were a lot of implementations. There was a lot of hardware support for it. So the question was what to do. And so the first thing that came to mind is, well, maybe we can take DES and we can kind of artificially expand the key size so we strengthen it against this exhaustive search attack. And the first idea that comes to mind is basically, well, let's iterate the block cipher a couple of times. And this is what's called triple DES. So triple DES is a general construction. Basically, it says the following. Suppose you give me a block cipher E. So here, it has a key space K, and it has a message space M, and an output space, of course, M as well. Let's define the triple construction, which now uses 3 keys. And it's defined as follows. Basically, here, the triple construction uses 3 independent keys, encrypts the same message block as before, and what it does is it will encrypt using the key K3, then it will decrypt using the key K2, and then it will encrypt again using the key K1. Okay, so it's basically encrypting 3 times using 3 independent keys. You might be wondering, why is it doing EDE? Why not just do EEE? Why do we have to have a D in the middle? Well, that's just for kind of a hack. You notice what happens if you set up K1 equals K2 equals K3? What happens if all 3 keys are the same? Well, basically, what would happen is one E and one D would cancel, and you would just get normal DES out. So it's just a hack so that if you have a hardware implementation of triple DES, you can set all 3 keys to be the same, and you'll get a hardware implementation of single DES. Of course, it'll be 3 times as slow as a regular implementation of single DES, but nevertheless, it's still an option. Okay, so for triple DES, in fact, now we get a key size that's 3 times 56, which is 168 bits. So this is 168 bits is way too long to actually do exhaustive search on. That will take time 2 to the 168, which is more than all the machines on Earth working for 10 years would be able to do. Unfortunately, of course, the cipher is 3 times slower than DES. So this is a real problem with triple DES. Now, I want to mention that, in fact, you might think that triple DES has security 2 to the 168, But in fact, there is a simple attack that actually runs in time 2 to the 118, and I want to show you how that attack works. Okay, so, but in fact, 2 to the 118 is still a large number. In fact, anything that's kind of bigger than 2 to the 90 is considered sufficiently secure. 2 to the 118 is definitely sufficiently secure against exhaustive search, and generally is considered a high enough level of security. So clearly, triple DES is 3 times as slow as DES. So the question is, why did they repeat the cipher 3 times? Why not repeat the cipher just 2 times? Or in particular, the question is, what's wrong with double DES? So here we have double DES. Basically, you see it uses only 2 keys, and it uses only 2 applications of the block cipher. And as a result, it's only going to be twice as slow as DES, not 3 times as slow as DES. Well, the key length for double DES is 2 times 56, which is 112 bits. And in fact, doing exhaustive search on a space of 112 bits is too much. 2 to the 112 is too big of a number to do exhaustive search over such a large space. So the question is, what's wrong with this construction? Well, it turns out this construction is completely insecure, and I want to show you an attack. So suppose I'm given a bunch of inputs, say M1 to M10, and I'm given the corresponding outputs C1 to C10. What's my goal? Well, my goal is basically to find keys, a pair of keys K1, K2, such that if I encrypt the message, the message capital M using these keys, in other words, if I do this encryption, this double DES encryption, then I get the ciphertext vector that was given to me. Okay, so our goal is to solve this equation here. Now you stare at this equation a little bit and you realize, hey, wait a minute, I can rewrite it in kind of an interesting way. I can apply the decryption algorithm, and then what I'll get is that I'm really looking for keys K1, K2 that satisfy this equation here, where basically all I did is I applied the decryption algorithm using K1 to both sides. Okay? Now, whenever you see an equation like this, what just happened here is that we separated our variables into 2 sides. The variables now appear on independent sides of the equation, and that usually means that there's a faster attack than exhaustive search. And in fact, this attack is called a meet-in-the-middle attack, where really the meet in the middle is going to somehow attack this particular point in the construction. Okay, so we're going to try and find a key that maps M to a particular value here and maps C to the same value. Okay, so let me show you how the attack works. So the first thing we're going to do is we're going to build a table. Here, let me clear up some space here. The first step is to build a table that for all possible values of K2 encrypts M under that value. Okay, so here we have this table. So you notice these are all, I'll say it like this, these are all 2 to the 56 DES keys, single DES keys. Okay, so the table has 2 to the 56 entries. And what we do is basically for each entry, we compute the encryption of M under the appropriate key. So this is the encryption of M under the all0 key, the encryption of M under the 1 key, and then at the bottom, we have the encryption of M under the all1 key. Okay, so there are 2 to the 56 entries, and we sort this table based on the second column. Okay, so far so good. So by the way, this takes time to build this table, takes time 2 to the 56, and I guess we also want to sort. Sorting takes n log n time, so it's 2 to the 56 times log 2 to the 56. Okay, so now that we have this table, we've essentially built all possible values in the forward direction for this point. Now what we're going to do is this meet in the middle attack, where now we try to go in the reverse direction with all possible keys K. Essentially, we compute the decryption of C under all possible keys K1. Okay, so now for each potential decryption, remember the table holds all possible values in the midpoint. So then for each possible decryption, we check, hey, is the decryption in the table, in the second column in the table? If it is in the table, then aha, we found a match. And then what do we know? We know that essentially, well, we found a match. So we know that, say, for example, a decryption using a particular key K1 happened to match this entry in the table, K sub 2 or more generally Ki, then we know that the encryption of M under Ki is equal to the decryption of C under K. Okay, so we kind of build this meet in the middle where the 2 sides, the encryption of M under Ki and the decryption of C under K collided. But if they collided, then we know that in fact this pair, Ki and K, is equal to the pair that we're looking for. And so we've just solved our challenge. So now let's look at what's the running time of this. Well, we had to build a table and then sort it. And then for all possible decryptions, we had to do a search through the table. So there were 2 to the 56 possible decryption. Each search in a sorted table takes log of 2 to the 56 time. If you just work it out, this turns out to be 2 to the 63, which is way smaller than 2 to the 112. Okay, so this is a serious attack. It's probably doable today. That runs in a total time of 2 to the 63, which is about the same time as the exhaustive search attack on DES. So really, double DES really didn't solve the exhaustive search problem because, well, there's an attack on it that runs in about the same time as exhaustive search on single DES. Now, someone might complain that in fact this algorithm, well, we have to store this big table, so it takes up a lot of space, but, you know, so be it. That's nevertheless, the running time is still quite smaller, significantly smaller than 2 to the 112. Now you notice, by the way, the same attack applies to triple DES. What you would do is you would implement a man-in-the-middle attack against this point. You would build a table of size 2 to the 56 of all possible encryptions of M, and then you would try to decrypt with all 2 to the 112 keys until you find a collision, and when you find a collision, you've basically found K1, K2, K3. Okay, so even triple DES has an attack that basically explores only 2 to the 112 possible keys. But 2 to the 112 is a large enough number, so triple DES, in fact, as far as we know, is sufficiently secure. I should mention that triple DES is actually a NIST standard, and so triple DES is actually used quite a bit, and in fact, DES should never, ever be used. If for some reason you're forced to use some version of DES, use triple DES, not DES. Okay, I want to mention one more method for strengthening DES against exhaustive search attacks. This method actually is not standardized by NIST because it doesn't defend against more subtle attacks on DES. But nevertheless, if all you're worried about is exhaustive search and you don't want to pay the performance penalties of triple DES, then this is an interesting idea. So let me show you how it works. So let E be a block cipher that operates on n-bit blocks. We're going to define the EX construction, and for DES we're going to get DESX to be the following. So we use 3 keys, K1, K2, K3, and then basically before encryption we XOR with K3, then we encrypt using K2, and then after encryption we XOR with K1. That's it. That's the whole construction. So basically, you notice it doesn't slow the block cipher much because all we did is we applied the cipher plus 2 additional XORs, which are super fast. The key length for this is in fact, well, we got 2 keys that are as long as the block size, and we got 1 key that's as long as the key size, so the total is 184 bits. Now, it turns out actually the best attack that's known is actually an attack that takes time 2 to the 120, and it's actually fairly simple. So it's a generic attack on EX. It will always take time, basically the block size plus the key size, and it's a simple homework problem for you to try to figure out this attack. I think this is a good exercise. Okay, in fact, there's some analysis to show that there is no exhaustive search attack on this type of construction. So it's a fine construction against exhaustive search, but there are more subtle attacks on DES that we'll talk about in the next segment that basically this construction will not prevent. One thing that I want to point out, unfortunately I found this mistake in a number of products, is if you just decide to XOR on the outside, or if you just decide to XOR on the inside, as opposed to XORing on both sides, which is what DESX does. You notice DESX XORs both on the outside and on the inside. If you just do one of them, then basically this construction does nothing to secure your cipher. It'll still be as vulnerable to exhaustive search as the original block cipher E. Okay, so this is another homework problem, and actually you'll see that as part of our homeworks. Okay, so this basically concludes our discussion of exhaustive search attacks, and next we'll talk about more sophisticated attacks on DES. There is an immense literature on attacking block ciphers. In this segment, I just want to give you a taste for what these attacks look like, and I hope I'll convince you that you should never, ever design your own block cipher and just stick to the standards like triple DES and AES. The first set of attacks I want to talk about are attacks on the implementation of the block cipher. As an example, imagine you have a smart card that's implementing a block cipher. So the smart card, for example, could be used for credit card payments. It might have a secret key inside of it to authenticate your credit card payments as you stick the card into a payment terminal, say. So now if an attacker obtains your smart card, what he could do is he could actually take the smart card to a lab and then run the card and measure very precisely how much time the card took to do encryption and decryption. Now, if the amount of time that the implementation took to do encryption depends on bits of the secret key, then by measuring the time, the attacker will learn something about your secret key, and in fact, he might even be able to completely extract your secret key. And there are many examples of implementations that simply by measuring the time very precisely for many operations of encryption algorithm, you can completely extract the secret key. Another example is rather than just measuring the time, you could actually measure the power consumption of the card as it's operating. So literally, you can connect it to a device that will measure the current that the card is drawing and then graph the current very, very precisely. Now, these cards are not very fast, and as a result, you can actually measure the exact amount of power consumed at every clock cycle as the card was executing. When you do that, you actually get graphs of this form. So this is an example of a smart card operating while it's doing the DIS computation. So you can see very clearly, here's when it was doing the initial permutation, here's when it's doing the final permutation, and then here you can count there are actually 16 hills and troughs corresponding to the 16 rounds. And essentially, when you zoom in on a graph like this, you can basically read the key bits off one by one just by looking at how much power the card consumed as it was doing the different operations. It turns out that even cards that take steps to mask this type of information are still vulnerable. There's an attack called a differential power analysis, where basically you measure the power consumed by the card over many runs of the encryption algorithm. And as long as there's any even small dependence between the amount of current consumed and the bits of the secret key, basically that dependence will show up after enough runs of the encryption algorithm, and as a result you'll be able to completely extract the secret key. Okay, so these attacks were actually discovered by Paul Kocher and his colleagues up at Cryptography3, and there's actually a fairly large industry devoted to just defending against these power attacks. As far as timing attacks are concerned, I want to mention that these are real. They're not just about smart cards. For example, you can imagine a multi-core processor where the encryption algorithm is running on one core and the attacker code happens to be running on another core. Now, these cores actually share the same cache, and as a result, an attacker can actually look at the exact cache misses that the encryption algorithm incurred. It turns out that by looking at cache misses, you can completely figure out the secret key used by the algorithm. So one core can essentially extract information from the other core just by looking at cache misses. So implementing these block ciphers is actually quite subtle because you have to make sure that the side channel attacks don't leak information about your secret key. Another type of attack that's been discussed in the literature is what's called a fault attack. So here, basically, if you're attacking a smart card, you can actually cause the smart card to malfunction, perhaps by overclocking it, perhaps by warming it up. Essentially, you can cause the processor to malfunction and output erroneous data. It turns out that if during encryption there are errors in the last round of the encryption process, that the resulting ciphertexts that are produced are enough to actually expose the secret key K. It's quite an interesting result that, in fact, if you have any errors, if you ever output a wrong result, that actually could completely compromise your secret key. So, of course, the defense against this means that before you output the result of your algorithm, you should check to make sure that the correct result was computed. Now, of course, that's non-trivial, because how do you know that the error didn't happen in your checking algorithm? But there are known ways around that. So basically, you can actually compute something 3 or 4 times, take majority over all those results, and be assured that the output really is correct, as long as not too many faults occurred inside of your computation. These are attacks on the implementation. I hope these examples kind of show you that not only should you not invent your own block ciphers, you should never even implement these crypto primitives yourself, because A, you have to make sure there are no side channel attacks on your implementation, and B, you have to make sure that the implementation is secure against fault attacks. Okay, so instead you should just use standard libraries like the ones available in OpenSSL and many other libraries out there. So don't implement these primitives yourself, just use existing libraries. Alright, so now I want to turn to kind of more sophisticated attacks on block ciphers, and I'll particularly talk about how these attacks apply to DES. Okay, so these attacks were discovered by Biham and Shamir back in 1989, and I'll particularly describe a version of the attack discovered by Matsui in 1993. So the goal here is basically, given many input-output pairs, can we actually recover the key better than exhaustive search? So anything that runs better than exhaustive search already counts as an attack on the block cipher. Okay, so the example I want to give you is what's called linear cryptanalysis. And here, imagine it so happens that C is the encryption of M using key K. And suppose it so happens that if I look at a random key and a random message, somehow there's a dependence between the message, ciphertext, and the key bits. In particular, if I XOR a subset of the message bits, so this is just a subset of the message bits, if I XOR that with a certain subset of the ciphertext bits, so these two the attacker sees. The attacker has the message and the attacker has the ciphertext. And then you compare that to an XOR of a subset of the key bits. Now, if the two were completely independent, which is what you'd like, you definitely don't want your message and your ciphertext to somehow predict your key bits. If the two are like completely independent, then this equality will hold with probability exactly 1/2. But suppose it so happens that there's a bias, and this probability holds with probability half plus epsilon for some small epsilon. It so happens that in fact for DES, there is such a relation. The relation holds specifically because of a bug in the design of the fifth S-box. It turns out the fifth S-box happens to be too close to a linear function, and that linear function basically, as it propagates through the entire DES circuit, generates a relation of this type. You notice this is basically a linear relation that's being computed here. So this small, tiny linearity in the fifth S-box generates this relation over the entire circuit where the epsilon is tiny. Epsilon is 1/2^21, and I wrote down what that is. So the bias is really small, but nevertheless there is a bias using these particular subsets of bits. Now I'm not going to show you how to derive this relation, or I'm not going to show you even what it is. I'll just tell you how to use a relation like this once you find it. Okay, so here's our relation that we have, and the question is how to use it. So with a little bit of statistics, you can actually use an equation like this to determine some of the key bits. And here's how you do it. Suppose you were given 1/epsilon² message ciphertext pairs, and these have to be independently random messages and the corresponding ciphertexts. What you would do is you would use the formula above. In fact, you would use the left-hand side of the formula above to compute this relation between the message and ciphertext for all the pairs you were given. Now, what do you know? You know that for half plus epsilon of these values, you know that these things will be equal to an XOR of the key bits. So if you take majority over all the values you've computed, it turns out it's not so difficult to see that in fact you'll get the correct prediction for the XOR of the key bits with probability 97.7%. In other words, if this relation happens to be correct more than half the time, then the majority will be right. And because there's a bias, there's an epsilon bias, the probability that you will be correct more than half the time is in fact 97.7%, in which case the majority in fact will give you the correct XOR of the key bits. Okay, so this is kind of cool. Within 1/epsilon² time, you can figure out an XOR of a bunch of key bits. So now let's apply this to DES. So for DES we have epsilon, which is 1/21, which means that if you give me 2^42 input-output pairs, I can figure out an XOR of the key bits. And now it turns out, I'm not going to exactly show you how, roughly speaking, using this method, you don't just get one key bit. In fact, you get two key bits. You can kind of use this relation. One's going in a forward direction and one's going in the backwards direction. So that gives you two XORs of bits of the secret key. Okay, so that's 2 bits of information about the secret key. And then it turns out you can get 12 more bits because essentially you can figure out what the inputs are to the fifth S-box. Okay, so I'm not going to exactly show you how, but it turns out you can get 12 more bits, which is a total of 14 bits overall. So now using this method, you've recovered 14 bits of the secret key, and of course it took you time 2^42. Okay, so then what do? Well, so the rest of it is easy. Now what you're going to do is you're going to do exhaustive search on the remaining bits. Well, how many remaining bits are there? Well, there are 42 remaining bits, so the exhaustive search would take you time 2^42. So what's the total attack time? Well, the first step of the algorithm to determine the 14 bits took 2^42 time, and the remaining brute force search also took 2^42 time. So overall, the attack took 2^43 time. Okay, so now this is much better than exhaustive search. Within 2^43 time, we broke DES, but of course this required 2^42 random input-output pairs, whereas exhaustive search only required 3 pairs. Okay, so this is a fairly large number of input-output pairs that are needed, but given such a large number, you can actually recover the key faster than exhaustive search. Okay, so what's the lesson in all this? The lesson is firstly, any tiny bit of linearity, basically in the fifth S-box, which was not designed as well as the other S-boxes, basically led to an attack on the algorithm. Okay, a tiny bit of linearity already introduced this linear attack. And I want to emphasize again that this is not the sort of thing you would think of when you design a cipher. And so again, the conclusion here is there are very subtle attacks on block ciphers, one which you will not be able to find yourself. And so just stick to the standards. Don't ever design your block cipher. Okay, so that's all I want to say about sophisticated attacks. Now let's move on to the last type of attack that I want to mention, which I'll call quantum attacks, which are again these are generic attacks on all block ciphers. So let me explain what I mean by this. So first of all, let's look at a generic problem. It's a generic search problem. Suppose I have a function on some large domain X that happens to output either 0 or 1. And it so happens that this function is mostly 0, and there's like maybe one input where the function happens to evaluate to 1. And your goal is basically, find me the input where the function happens to be 1. Maybe there's only one such input, but your goal is to find it. Well, so on a classical computer, what can you do? The function is given to you. It's given to you as a black box. So the best you can do is just try all possible inputs. So this is going to take time, which is linear in the size of the domain. Now, it turns out there's an absolutely magical result that says that if you build a computer that's based on quantum physics as opposed to classical physics, you can solve this problem faster. So let me explain what I mean by this. So first of all, in the 70s and 80s, it was observed, I think it was actually Richard Feynman who observed this initially, that said that it turns out to be very difficult to simulate quantum experiments on a classical computer. So Feynman said, hey, if that's the case, maybe these quantum experiments are computing things that a classical computer can't compute. So they're somehow able to compute very quickly things that are very difficult to do classically. And that turned out to be correct. And in fact, the example I want to show you is one of these amazing things that, in fact, if you could build a quantum computer that's using quantum physics, then in fact you can solve this search problem not in time x, but in time square root of x. So somehow, even though the computer doesn't know anything about the function f, it's treating it as a black box, nevertheless it's able to find a point when the function is 1 in time square root of x. I'm not going to explain this here, but at the end of the class we're going to have an advanced topics lecture, and if you'd like me to explain how this algorithm works, I can explain it in that advanced topics lecture. It's actually quite interesting, and in fact quantum computers have quite an impact on crypto, and again, as I said, I can explain this in the very last lecture. Alright, so what does this have to do with breaking block ciphers? So far it's just a generic search problem. Well, actually I guess I should say before I show you the application, I should mention that, well, you might be wondering, well, can someone build a quantum computer? And this is still completely unknown. But at this point, nobody really knows if we can build large enough quantum computers to actually take advantage of this beautiful algorithm due to Grover. All right, so what does this have to do with block ciphers? Well, so suppose I give you a message and a ciphertext pair. Just one or just a few. We can define a function as follows. It's a function on K. It's a function on the key space. And the function will basically output 1 if it so happens that the encryption of M with K maps to C, and it will output 0 otherwise. Now we argue that basically this is exactly the type of function that's 1 at one point in the key space, and that's it. So by Grover's algorithm, we can actually find the secret key in times square root of K. So what does that mean? For DES, this would totally destroy DES. This would say that in time 2 to the 28, you can find a key. 2 to the 28 is about 200 million, so 200 million steps, which is, this takes a millisecond on a modern computer. This would totally destroy DES. But even AES with 128-bit keys, you would be able to find the secret key in time roughly 2 to the 64. And 2 to the 64 is these days considered insecure. That's within the realm of exhaustive search. And so basically, if somebody was able to build a quantum computer, we would then say that AES 128 is no longer secure. Instead, if somebody, if tomorrow you open up the newspaper and you read an article that says, so-and-so built a quantum computer, the consequence of all that is that you should immediately move to block ciphers that use 256 bits, because then the running time of Grover's algorithm is 2 to the 128, which is more time than we consider feasible. And basically, there are example ciphers with 256 bits, for example, AES 256. This is one of the reasons why AES was designed with 256 bits in mind, but to be honest, this is not the only reason. There are other reasons why you wanted to have larger key sizes. Okay, so this is, as I said, just a taste of the different attacks on block ciphers, And I'm going to leave it at that. If we decide on quantum for the last topic of the course, then we'll cover that in the very last lecture. Over the years, it became clear that DES and triple DES are simply not designed for modern hardware and are too slow. As a result, NIST started a new process to standardize on a new block cipher called the Advanced Encryption Standard, or AES for short. NIST started this effort in 1997 when it requested proposals for a new block cipher. It received 15 submissions a year later, and finally in the year 2000 it adopted the cipher called Rindel as the Advanced Encryption Standard. This was a cipher designed in Belgium, and we already said that its block size is 128 bits, and it's got three possible key sizes: 128 bits, 192, and 256. And now the assumption is that the larger the key size is, the more secure the block cipher is as a pseudo-random permutation. But because it also has more rounds involved in its operation, the slower the cipher becomes. So the larger the key, supposedly the more secure the cipher, but also the slower it becomes. So for example, AES 128 is the fastest of these ciphers, and AES 256 is the slowest. Now, AES is built as what's called a substitution permutation network. It's not a Feistel network. Remember that in a Feistel network, half the bits were unchanged from round to round. In a substitution permutation network, all the bits are changed in every round, and the network works as follows. So here we have the first round of the substitution permutation network, where the first thing we do is we XOR the current state with the round key, in this case the first round key. Then we go through a substitution layer where blocks of state are replaced with other blocks based on what the substitution table says. And then we go through a permutation layer where bits are permuted and shuffled around. And then we do this again. We XOR with the next round key, we go through a substitution phase, and we permute the bits around. And so on and so on and so forth until we reach the final round where we XOR with the very last round key, and then out comes the output. Now, an important point about this design is that, in fact, because of how it's built, every step in this network needs to be reversible so that the whole thing is reversible. And so the way we would decrypt, essentially, is we would take the output and simply apply each step of the network in reverse order. So we start with the permutation step, and we have to make sure that step is reversible. Then we look at the substitution layer, and we have to make sure this step is reversible. And this is very different from DES. In DES, if you remember, the substitution tables were not reversible at all. In fact, they mapped 6 bits to 4 bits, whereas here, everything has to be reversible, otherwise it would be impossible to decrypt. And of course, the XOR with the round key is reversible as well. Okay, so inversion of a substitution permutation network is simply done by applying all the steps in the reverse order. So now that we understand the generic construction, let's look at the specifics of AES. So AES operates on a 128-bit block, which is 16 bytes. So what we do with AES is we write those 16 bytes as a 4x4 matrix. Each cell in the matrix contains 1 byte. And then we start with the first round. So we XOR with the first round key. And then we apply a certain function that includes substitutions and permutations and other operations on the state. And again, these 3 functions that are applied here have to be invertible so that, in fact, the cipher can be decrypted. And then we XOR with the next round key, and we do that again. Again, we apply the round function and XOR with the round key, and we do that again and again and again. We do it 10 times, although interestingly, in the last round, the mixed column step is actually missing. And then finally, we XOR with the last round key, and out comes the output. Again, at every phase here, we always keep this 4x4 array, and so the output is also 4x4, which is 16 bytes, which is 128 bits. Now, the round keys themselves, of course, come from a 16-byte AES key using key expansion. So the key expansion maps us from a 16-byte AES key into 11 keys, each one being 16 bytes. So these keys themselves are also a 4x4 array that's XORed into the current state. Okay, so that's the schematic of how AES works, and the only thing that's left to do is specify these 3 functions: byte sub, shift row, and mixed column. And those are fairly easy to explain, so I'm just going to give you the high-level description of what they are, and those interested in the details can look it up online. So the way byte substitution works is literally it's one S box containing 256 bytes, and essentially what it does is it applies the S box to every byte in the current state. So let me explain what I mean by that. So the current state is going to be this 4x4 table. So here we have the 4x4 table. And to each element in this table, we apply the S box. So let's call it the A table. And then what we do is essentially for all 4x4 entries, essentially the next step, Aij, becomes the current step evaluated at the lookup table. So we use the current cell as an entry, as an index into the lookup table, and then the value of the lookup table is what's output. Okay, so that's the first step. The next step that happens is a shift row step, which is basically just a permutation. So essentially, we kind of do a cyclic shift on each one of the rows. So you can see the second row is cyclically shifted by 1 position, the third row is cyclically shifted by 2 positions, and the third row is cyclically shifted by 3 positions. And the last thing we do is mix columns, where literally we apply a linear transformation to each one of these columns. So there's a certain matrix that multiplies each one of these columns, and it becomes the next column. So this linear transformation is applied independently to each one of the columns. Now I should point out that so far shift rows and mixed columns are very easy to implement in code, and I should say that the byte substitution itself is also easily computable, so that you can actually write code that takes less than 256 bytes to write, and you can kind of shrink the description of AES by literally storing code that computes the table rather than hardwiring the table into your implementation. And in fact, this is kind of a generic fact about AES, that if you kind of allow no pre-computation at all, including computing the S box on the fly, then in fact you get a fairly small implementation of AES, so it could fit on very constrained environments where there isn't enough room to hold complicated code. But of course this would be the slowest implementation because everything is computed now on the fly, and as a result the implementation obviously is going to be slower than if things were pre-computed. And then there's this trade-off. For example, if you have a lot of space and you can support large code, you can actually pre-compute quite a bit of the 3 steps that I just mentioned. In fact, there are multiple options of pre-computations. You can build a table that's only 4 kilobyte big, or you can build a table that's even longer, maybe 24 kilobytes. So basically you'll have these big tables in your implementation, but then your actual performance is going to be really good because all you're doing is just table lookups and XORs. You're not doing any other complicated arithmetic. And as a result, if you can do a lot of pre-computation, these 3 steps here, byte sub, shift rows, and mixed columns, can be converted just into a small number of table lookups and some XORs. All you can do is just compute the S box, so now your implementation would just have 256 bytes hard-coded. The rest would just be code that's actually computing these 3 functions. The performance would be slower than in the previous step, but the code footprint would also be smaller. So, and overall, there's this nice trade-off between code size and performance. So on high-end machines, on high-end servers, where you can afford to have a lot of code, you can pre-compute and store these big tables and get the best performance. Whereas on low-end machines like 8-bit smart cards, or think of like an 8-bit wristwatch, you would actually have a relatively small implementation of AES, but as a result, of course, it won't be so fast. So here's an example that's a little unusual. Suppose you wanted to implement AES in JavaScript, so you can send an AES library to the browser and have the browser actually do AES by itself. So in this case, what you'd like to do is you'd like to both shrink the code size so that on the network there's minimum traffic to send the library over to the browser, but at the same time you'd like the browser performance to be as fast as possible. So this is something that we did a while ago. Essentially the idea is that the code that actually gets sent to the browser doesn't have any pre-computed table, and as a result it's fairly small code, but then the minute it lands on the browser, what the browser will do is it will actually pre-compute all the tables. So in some sense the code goes from this being small and compact, it gets bloated with all these pre-computed tables, but those are stored on the laptop, which presumably has a lot of memory. And then once you have the pre-computed tables, you actually encrypt using them, and that's how you get the best performance. Okay, so if you have to send an implementation of AES over the network, you can kind of get the best of all worlds, where the code over the network is small, but when it reaches the target client, it can kind of inflate itself and then get the best performance as it's doing encryption on the client. Now, AES is such a popular block cipher. Now, essentially, when you build crypto into products, essentially you're supposed to be using AES. And as a result, Intel actually put AES support into the processor itself. So since Westmere, there are special instructions in the Intel processor to help accelerate AES. And so I listed these instructions here. They come in two pairs, AES enc and AES enc last, and then there's AES keygen assist. So let me explain what they do. So AES enc essentially implements one round of AES, namely apply the three functions in the XOR with the round key. And AES enc last basically implements the last round of AES. Remember, the last round didn't have the mixed columns phase. It only had the subs bytes and shift rows. And so that's what AES enc last does. And the way you call these instructions is using 128-bit registers, which correspond to the state of AES. And so you would have one register containing the state and one register containing the current round key. And then when you call AES enc on these two registers, basically they would run one round of AES and place the result inside of this XMM1 state register. And as a result, if you wanted to implement the whole AES, all you would do is you would call AES enc 9 times, and then you would call AES enc last 1 time, and these 10 instructions are basically the entire implementation of AES. That's it. It's that easy to implement AES on this hardware. And they claim because these operations are now done inside the processor, not using external instructions, they're implemented in the processor, they claim that they can get a 14x speed up over, say, an implementation that's running on the same hardware, but implementing AES without these special instructions. So this is quite a significant speed up, and in fact there are now lots of products that make use of these special instructions. And let's just say that this is not specific to Intel. If you're an AMD fan, AMD also implemented exactly kind of similar instructions in their Bulldozer architecture and further in future architectures. Okay, so let's talk about the security of AES. I want to mention just two attacks here. Obviously, AES has been studied quite a bit, but the only two attacks on the full AES are the following two. So first of all, if you wanted to do key recovery, the best attack basically is only 4 times faster than exhaustive search, which means that instead of a 128-bit key, really you should be thinking of AES as a 126-bit key, because exhaustive search really is kind of 4 times faster than it should. Of course, 2 to the 126 is still more time than we have to compute, and this really does not hurt the security of AES. The more significant attack actually is on AES 256. It turns out there's a weakness in the key expansion design of AES, which allows for what's called a related key attack. So what's a related key attack? Essentially, if you give me about 2 to the 100 input-output pairs for AES, but from 4 related keys. So these are keys that are very closely related. Namely, key number 2 is the same as key number 1, except that a few bits of key number 1 have been flipped. Similarly, key number 3 is the same as key number 1, except that a few bits are flipped, and the same for key number 4. These are very closely related keys. If you like, their Hamming distance is very short. But if you do that, then in fact, there is a 2 to the 100 attack. Now you should say, well, 2 to the 100 is still impractical. This is still more time than we can actually run today. But nevertheless, the fact that it's so much better than an exhaustive search attack is so much better than 2 to the 256 is kind of a limitation of the cipher. But generally, it's not a significant limitation because it requires related keys. And so in practice, of course, you're supposed to be choosing your keys at random so that you have no related keys in your system, and as a result, this attack wouldn't apply. But if you do have related keys, then there's a problem. So this is the end of the segment, and in the next segment, we're going to talk about more provably secure constructions for block ciphers. In this segment, we ask whether we can build block ciphers from simpler primitives like pseudorandom generators. And we're going to show that the answer is yes. So to begin with, let's ask whether we can build pseudorandom functions as opposed to pseudorandom permutations from a pseudorandom generator. Okay? Can we build a PRF from a PRG? Our ultimate goal, though, is to build a block cipher, which is a PRP. And we'll get to that at the end. Okay, for now we build a PRF. So let's start with a PRG that doubles its input. Okay, so the seed for this PRG is an element in K, and the output is actually 2 elements in K. So here we have a schematic of this generator that basically takes as input a seed in K and outputs 2 elements in K as its output. And now what does it mean for this PRG to be secure? Recall, this means that essentially the output is indistinguishable from a random element inside of K squared. Now it turns out it's very easy to define basically what's called a 1-bit PRF from this PRG. So what's a 1-bit PRF? It's basically a PRF whose domain is only 1 bit. Okay, so it's a PRF that just takes 1 bit as input. Okay, and the way we'll do it is we'll say if the input bit x is 0, output the left output, and if the input bit x is 1, output the right output of the PRF. Okay, in symbols, basically we have what we wrote here. Now it's straightforward to show that in fact if G is a secure PRG, then this 1-bit PRF is in fact a secure PRF. If you think about it for a second, this is really a tautology. It's really just stating the same thing twice. So I'll leave it for you to think about this briefly and see and convince yourself that in fact this theorem is true. The real question is whether we can build a PRF that actually has a domain that's bigger than just 1 bit. Ideally, we'd like the domain to be 128 bits, just say as AES has. So the question is, can we build a 128-bit PRF from a pseudo-random generator? Well, so let's see if we can make progress. So the first thing we're going to do is we're going to say, well, again, let's start with a PRG that doubles its input. Let's see if we can build a PRG that quadruples its input. Okay, so it goes from k to the 4th instead of k to k squared. Okay, so let's see how to do it. So here we start with our original PRG that just doubles its input. But now remember, the fact that this is a PRG means that the output of the PRG is indistinguishable from 2 random values in k. Well, if the output looks like 2 random values in k, we can simply apply the generator again to those 2 outputs. So let's say we apply the generator once to the left output and once to the right output. And we're going to call the output of that, this quadruple of elements, we're going to call that G1k. And I wrote down in symbols what this generator does, but you can see basically from this figure exactly how the generator works. Okay, so now that we have a generator from k to the 4th, we actually get a 2-bit PRF. Namely, what we'll do is we'll say, given 2 bits, 0, 0, 0, 1, 1, 0, or 1, 1, we'll simply output the appropriate block that's the output of G1k. Okay, so now we can basically have a PRF that takes 4 possible inputs as opposed to just 2 possible inputs as before. So the question you should be asking me is, why is this G1k secure? Why is it a secure PRG? That is, why is this quadruple of outputs indistinguishable from random? And so let's do a quick proof of this. We'll just do a simple proof by pictures. So here's our generator that we want to prove is secure. And what that means is we want to argue that this distribution is indistinguishable from a random 4-tuple in k to the 4th. Okay, so our goal is to prove that these 2 are indistinguishable. Well, let's do it one step at a time. We know that the generator is a secure generator. Therefore, in fact, the output of the first level is indistinguishable from random. In other words, if we replace the first level by truly random strings, these 2 are truly random picked in the key space, then no efficient adversary should be able to distinguish these 2 distributions. In fact, if you could distinguish these 2 distributions, it's easy to show that you would break the original PRG. Okay, but essentially you can see that the reason we can do this replacement, we can replace the output of G with truly random values, is exactly because of the definition of the PRG, which says that the output of the PRG is indistinguishable from random, so we might as well just put random there, and no efficient adversary can distinguish the resulting 2 distributions. Okay, so far so good. But now we can do the same thing again to the left-hand side. In other words, we can replace these 2 pseudo-random outputs by truly random outputs. And again, because the generator G is secure, no efficient adversary can tell the difference between these 2 distributions. Put differently, if an adversary can distinguish these 2 distributions, then we would also get an attack on the generator G. And now finally, we're going to do this one last time. We're going to replace this pseudo-random pair by a truly random pair, and then lo and behold, we get the actual distribution that we were shooting for. We will get a distribution that's really made of 4 independent blocks. And so now we've proved this transition basically that these 2 are indistinguishable, these 2 are indistinguishable, and these 2 are indistinguishable, and therefore these 2 are indistinguishable, which is what we wanted to prove. Okay, so this is kind of the high-level idea for the proof. It's not too difficult to make this rigorous, but I just wanted to show you kind of the intuition for how the proof works. Well, if we were able to extend the generator's output once, there's nothing preventing us from doing it again. So here's a generator G1 that outputs 4 elements in the key space. And remember, the output here is indistinguishable from a random 4-tuple. That's what we just proved. And so there's nothing preventing us from applying the generator again. So we'll take the generator, apply it to this random looking thing, and we should be able to get this random looking thing, this pair over here that's random looking. And we can do the same thing again and again and again. And now basically we've built a new generator that outputs elements in k to the 8th as opposed to k to the 4th. And again, the proof of security is pretty much the same as the one I just showed you. Essentially, you gradually change the outputs into truly random outputs. So we would change this to a truly random output, then this, then that, then this, then that, and so on and so forth. Until finally we get something that's truly random, and therefore the original two distributions we started with, G2K and truly random, are indistinguishable. Okay, so far so good. So now we have a generator that outputs elements in k to the 8th. Now if we do that, basically we get a 3-bit PRF. In other words, at 0, 0, 0, this PRF would output this block, and so on and so forth, until 1, 1, 1, it would output this block. Now the interesting thing is that in fact this PRF is easy to compute. So for example, suppose we wanted to compute the PRF at the point 1, 0, 1. Okay, it's a 3-bit PRF. So 1, 0, 1. How would we do that? Well, basically we would start from the original key k, and now we would apply the generator g, but we would only pay attention to the right output of g, because the first bit is 1. And then we will apply the generator again, but we would only pay attention to the left output of the generator, because the second bit is 0. And then we would apply the generator again and only pay attention to the right outputs, because the third bit is 1, and that would be the final output. Right? So you can see that that led us to 1, 0, 1, and in fact, because the entire generator is pseudorandom, we know in particular that this output here is pseudorandom. Okay, so this gives us a 3-bit PRF. Well, if it worked 3 times, there's no reason why it can't work n times. And so if we apply this transformation again and again, we arrive at what's called the GGM PRF. GGM stands for Goldreich, Goldwasser, and Micali. These are the inventors of this PRF. And the way it works is as follows. So we start off with a generator that just doubles its output. And now we're able to build a PRF that acts on a large domain, namely a domain of size 0, 1 to the n, where n could be as big as 128 or even more. So let's see. Suppose we're given an input in 0, 1 to the n. Let me show you how to evaluate the PRF. Well, by now you should actually have a good idea for how to do it. Essentially, we start from the original key, and then we apply the generator, and we take either the left or the right side, depending on the bit x0. And then we arrive at the next key, k1. And then we apply the generator again, and we take the left or the right side, depending on x1, and we arrive at the next key. And then we do this again and again, until finally we arrive at the output. So we've processed all n bits, and we arrive at the output of this function. And basically, we can prove security, again, pretty much along the same lines as we did before. And we can show that if G is a secure PRG, then in fact we get a secure PRF on 0, 1 to the n, on a very large domain. So that's fantastic. So now we have, essentially, we have a PRF that's provably secure, assuming the underlying generator is secure. And a generator is supposedly much easier to build than an actual PRF. And in fact, it works on blocks that could be very large, in particular 0, 1 to the 128, which is what we needed. So you might ask, well, why is this thing not being used in practice? And the reason is that it's actually fairly slow. So imagine we plug in as a generator, imagine we plug in the salsa generator. So now to evaluate this PRF at 128-bit input, we would basically have to run the salsa generator 128 times, 1 time per bit of the input. But then we would get a PRF that's 128 times slower than the original salsa, and that's much, much, much slower than AES. AES is a heuristic PRF, but nevertheless, it's much faster than what we just got here. And so even though this is a very elegant construction, it's not used in practice to build pseudorandom functions, although in a week we will be using this type of construction to build a message integrity mechanism. So the last step is basically, now that we have built a PRF, the question is whether we can actually build a block cipher. In other words, can we actually build a secure PRP from a secure PRG? Everything we've done so far is not reversible. Again, if you look at this construction here, we can't decrypt. Basically, given the final output, it's not possible to go back, or at least we don't know how to go back to the original input. So now the question of interest is, can we actually solve the problem we wanted to solve initially? Namely, can we actually build a block cipher from a secure PRG? So I'll let you think about this for a second and mark the answer. So of course I hope everybody said the answer is yes, and you already have all the ingredients to do it. In particular, you already know how to build a PRF from a pseudorandom generator. And we said that once we have a PRF, we can plug it into the Luby-Rokov construction, which, if you remember, was just a 3-round Feistel. So we said that if you plug a secure PRF into a 3-round Feistel, you get a secure PRP. So combining these two together basically gives us a secure PRP from pseudorandom generator. And this is provably secure as long as the underlying generator is secure. So it's a beautiful result, but unfortunately, again, it's not used in practice because it's considerably slower than heuristic constructions like AES. Okay, so this completes our module on constructing pseudorandom permutations and pseudorandom functions. And then in the next module, we're going to talk about how to use these things to do proper encryption.